Imagine a single teaspoon of cosmic material so powerful it could erase every hard drive, phone, and digital memory on Earth in an instant. This isn't science fiction, it's the reality of magnetars, the universe's most terrifyingly magnetic monsters. Born from the ashes of exploding stars, these cosmic anomalies pack magnetic fields quadrillions of times stronger than Earth's, warping the fabric of space around them like invisible fists. Picture a dying star collapsing into a city-sized orb so dense, a sugar cube of its material would weigh as much as a mountain. Now crank its magnetic pull to levels that twist atoms into spaghetti from halfway across the galaxy. This is the realm of magnetars where physics textbooks surrender and reality gets weird. Over the next few minutes, we'll venture into their lethal magnetic storms, decode their explosive tantrums that outshine whole galaxies, and reveal why spotting one in our cosmic neighborhood would rewrite life as we know it. Buckle up, we're diving into the most extreme physics laboratory the universe has ever built. Now let's peel back the layers of these cosmic monsters to understand what truly makes a magnetar. At their core, magnetars are neutron stars, stellar remnants left behind after massive stars go supernova. But they're not your average neutron stars. Imagine taking the already mind-bending density of a neutron star, where a single teaspoon of material weighs as much as Mount Everest, and then cranking its magnetic field to unimaginable levels. That's a magnetar. To grasp just how intense their magnetism is, let's put it in perspective. Earth's magnetic field is strong enough to guide compass needles it clocks in at about 0.5 Gauss. A typical fridge magnet, around 50 Gauss. Now hold onto your seat because a magnetar's magnetic field can reach up to 10 quadrillion Gauss. That's a 1 followed by 16 zeros. If a magnetar sat halfway between Earth and the Moon, its magnetic pull would strip the data from every credit card on our planet, and if you somehow got within 1,000 miles of one, the magnetic forces would literally tear your atoms apart, reshaping your very molecular structure like cosmic taffy. But their terror doesn't stop there. Magnetars are tiny by cosmic standards, only about 12 miles in diameter, yet they pack more mass than our Sun. Picture squeezing 500,000 Earths into a ball the size of Manhattan. Inside, the pressure is so extreme that protons and electrons merge, creating a soup of neutrons and exotic particles scientists can only theorize about. Some models suggest their cores might contain quark-gluon plasma, a state of matter so strange it hasn't existed naturally since the first milliseconds after the Big Bang. What's wild is that we've barely scratched the surface of understanding these objects. Out of the billions of neutron stars in our galaxy, only around 30 have been confirmed as magnetars. Their magnetic fields are so strong they actually slow the star's spin over time, sapping its energy like a cosmic break. And occasionally, when their crusts crack under the strain, a phenomenon called a starquake, they unleash bursts of radiation so powerful they can be detected clear across the galaxy. But we'll dive deeper into those explosive tantrums later. For now, just remember, if you ever stumble upon a magnetar, the last thing you'll worry about is your credit card. Your atoms will be too busy unraveling. Now let's rewind the cosmic clock to witness the explosive birth of a magnetar. These magnetic monsters don't just appear out of nowhere, they're forged in the heart of chaos, born from the death throes of massive stars. Picture a star at least 8 times heavier than our Sun, burning through its fuel at a furious pace. When it finally runs out of nuclear firepower, gravity wins the battle, and the star collapses in on itself in a cataclysmic supernova explosion. What's left behind isn't just a corpse, it's a reborn entity with a magnetic personality unlike anything else in the universe. Here's where things get wild. As the star implodes, its core, now a neutron star, spins up to dizzying speeds, sometimes rotating hundreds of times per second. But for a select few, something extraordinary happens. The turbulent soup of charged particles inside, coupled with the star's rapid rotation, creates a cosmic generator known as the dynamo effect. Think of it like a hypercharged version of Earth's molten core, but instead of creating a gentle magnetic field, this dynamo cranks the magnetism to levels that defy logic. In mere seconds, the newborn star's magnetic field amplifies to intensities that would make even sci-fi writers blush. What sets magnetars apart from their neutron star cousins like pulsars? It's all about attitude. Pulsars are the disciplined athletes of the neutron star world, spinning with predictable rhythm, emitting steady beams of radiation like cosmic lighthouses. Magnetars, on the other hand, are the volatile artists. Their magnetic fields are thousands of times stronger, and they're prone to dramatic outbursts. While a pulsar's energy comes from its spin, a magnetar's power is locked in its monstrous magnetic field, which can twist and snap like an overwound rubber band, unleashing devastating bursts of energy. The formation process is so extreme that only about 1 in 10 supernova explosions produces a magnetar. It's a cosmic lottery where the winning ticket requires the perfect storm of mass, spin, and magnetic mayhem. And here's a mind-bending detail. Some scientists believe magnetars might start life as hypermagnetic pulsars before their fields intensify. Others speculate that collisions between neutron stars could birth them. Either way, their creation is a reminder that the universe specializes in turning destruction into something breathtakingly powerful. So the next time you look up at the night sky, remember, somewhere out there, a dying star's final act might be creating the ultimate magnetic marvel. Now let's peel back the layers of a magnetar's magnetic might and see what makes it tick. At their core, these objects are essentially giant cosmic electromagnets, but with a twist that pushes physics to its limits. Imagine taking everything you know about magnets and cranking it up to a quadrillion. That's the scale we're dealing with here. The secret lies in the bizarre behavior of matter under such extreme conditions. Inside a magnetar, protons and electrons aren't just floating around, they're locked in a high-speed dance, forced to play by the rules of quantum mechanics. Protons in the star's core become superconducting, meaning they can carry electric currents with zero resistance. Picture a highway where cars, or in this case, charged particles, zip along without ever hitting traffic. Meanwhile, electrons swirl like a frenzied whirlpool, generating currents that loop and twist. Together, these movements create a self-sustaining magnetic field, one that feeds off the star's insane rotation. It's like a turbine in a power plant, except this turbine spins at nearly the speed of light, and its wires are made of star stuff compressed to unimaginable densities. Here's where quantum mechanics and astrophysics collide in the most spectacular way. Under normal conditions, magnetic fields have limits, a point where they'd fizzle out or collapse. But in a magnetar, the density is so extreme that the usual rules don't apply. The star's core is packed so tightly that a sugar cube-sized chunk of it would weigh more than Mount Everest. That density, combined with the star's rapid spin, acts like a feedback loop, amplifying the magnetic field to levels that shouldn't even exist. It's as if the universe took a physics textbook, scribbled over the equations, and said, "Watch this." To put this in perspective, think of Earth's magnetic field as a gentle breeze enough to guide a compass needle. A typical neutron star's field, that's a hurricane. But a magnetar's field is more like a hypercharged solar storm, capable of distorting the very shape of atoms. If you could get close enough, which you absolutely shouldn't, the magnetic force would literally pull electrons off your body before you even realized what was happening. And here's the kicker, these fields aren't static. They're alive, constantly shifting and cracking under their own pressure. When the crust of a magnetar fractures, a phenomenon called a starquake, it releases pent-up magnetic energy in bursts so powerful they can be detected across galaxies. That's the universe reminding us that even in the coldest corners of space, there's nothing quiet about magnetism when it's pushed to the extreme. So the next time you hold a fridge magnet, remember, somewhere out there, its cosmic cousin is bending the laws of physics just by existing. Now let's shift gears and pit these magnetic monsters against another cosmic heavyweight, the black hole. At first glance, they might seem like distant cousins in the stellar family tree, but the differences between them are as stark as night and day. Both are born from the fiery demise of massive stars, yet their paths diverge spectacularly from there. When a star collapses, its fate hinges on mass. A star weighing between 8 and 30 times our Sun becomes a neutron star, and if conditions are just right, a magnetar. But if it's heavier, gravity wins the ultimate tug of war, crushing everything into a black hole. Think of it like baking a cake. The ingredients might be similar, but the outcome depends on the recipe. Magnetars retain some structure, packing their matter into a city-sized sphere so dense it defies logic. Black holes, on the other hand, don't stop at defying logic. They erase it. Their gravity is so intense that not even light can escape, creating a point of no return, the event horizon. Magnetars might twist atoms with their magnetic fields, but black holes make spacetime itself buckle. Now, let's talk visibility. Magnetars are cosmic lighthouses, flashing their presence across the universe with X-rays and gamma rays. These bursts are like fingerprints, letting astronomers study them from millions of light years away. Black holes, by contrast, are the ultimate introverts. They don't emit light, only revealing themselves by how they affect their surroundings, like the glowing disk of doomed matter spiraling into them, or the gravitational waves they send rippling through the cosmos when they collide. So which one would you rather avoid in your interstellar neighborhood? Magnetars unleash sporadic but devastating flares like the one in 2004 that temporarily scrambled Earth's ionosphere from halfway across the galaxy. Get too close and their magnetic fields would shred your molecules. Black holes are more patient but no less deadly. Their gravity stretches you into a noodle of atoms in a process hilariously named spaghettification, all before you vanish forever. But here's the twist: magnetars don't last. Their magnetic fields decay over millennia, leaving behind a quieter neutron star. Black holes are eternal, growing larger as they devour everything in their path. So while a magnetar might be the universe's most volatile electromagnet, a black hole is its ultimate abyss. The verdict neither makes for a good neighbor, but if you had to choose, at least with a magnetar, you'd see the fireworks coming. Next time you gaze at the night sky, remember this cosmic duel. One bends the rules, the other rewrites them entirely. And both remind us that in the grand theater of the universe, the most extreme players rarely follow the script. Now let's turn our attention to another jaw-dropping spectacle in the life of a magnetar: starquakes. Imagine the ground beneath your feet suddenly cracking open, unleashing unimaginable energy. Now multiply that by 1 trillion and you've got a starquake. These aren't your average tremors. When a magnetar's crust fractures under the strain of its own magnetic field, it's like the universe's most violent tantrum, releasing energy that can outshine entire galaxies for a fraction of a second. The science behind these events is as wild as they sound. Magnetars are so dense that their crusts are made of crystalline neutron material far stronger than anything on Earth. But even that can't withstand the twisting forces of their magnetic fields. Picture a rubber band stretched to its limit. When it snaps, all that stored energy explodes outward. In a magnetar's case, the snap is a starquake, and the energy released is enough to ripple spacetime itself, sending gravitational waves across the cosmos. But here's where it gets even crazier. These starquakes don't just shake the magnetar, they light up the sky with bursts of X-rays and gamma rays. One of the most famous examples happened in December 2004, when a magnetar 50,000 light-years away, known as SGR 1806-20, unleashed a flare so powerful it briefly outshone the Moon. For a fifth of a second, it carried more energy than our Sun has emitted in the past 250,000 years. The burst was so intense it actually ionized Earth's upper atmosphere, disrupting radio communications and even affecting satellites. If that magnetar had been just a few tens of light years closer, the effects could have been catastrophic. What's truly mind-bending is how these starquakes warp the very fabric of reality. Einstein's theory of relativity tells us that massive objects can bend spacetime, but magnetars take it to another level. When their crusts shift, they create gravitational waves, ripples in spacetime that detectors like LIGO and Virgo are designed to catch. Think of it as dropping a boulder into a pond, except the pond is the universe and the ripples travel at the speed of light. So why should we care about these distant cosmic tantrums? Because they're like nature's own particle accelerators, giving us a front row seat to physics that we could never recreate on Earth. Every starquake is a clue helping scientists unravel the mysteries of extreme magnetism, dense matter, and the very laws that govern our universe. And while we might not see one up close anytime soon, knowing they're out there twisting, shaking, and lighting up the cosmos reminds us just how dynamic and unpredictable the universe can be. Next time you hear about a distant flash of gamma rays, remember, it might just be a magnetar throwing a fit, reminding us all who's really in charge out there. Now let's zoom in on another breathtaking display of magnetar fury gamma-ray flares. If starquakes are the universe's tantrums, these flares are its fireworks, and they're some of the most violent explosions since the Big Bang itself. Picture the energy of a million suns crammed into a fraction of a second, and you're starting to grasp the sheer scale of these cosmic outbursts. What causes these staggering bursts of energy? Scientists have two leading theories. The first involves magnetic reconnection, a process where twisted magnetic field lines snap and realign, releasing colossal amounts of energy, like a cosmic rubber band finally giving way. The second theory points to crust-shattering, where the magnetar's surface fractures under immense magnetic stress, unleashing a torrent of gamma rays. Both scenarios are like a pressure cooker exploding, except the cooker is a city-sized star with a magnetic field strong enough to rip atoms apart. One of the most extreme examples occurred in December 2004, when SGR 1806-20 erupted in a flare so bright it temporarily outshone the Moon. For just a fifth of a second, this single magnetar released more energy than our Sun pumps out in 250,000 years. The blast was so intense it ionized Earth's upper atmosphere from 50,000 light-years away, disrupting radio signals and even affecting satellites. If this had happened within 20 light-years of us, it could have stripped away our ozone layer, triggering a mass extinction. But here's where it gets even more fascinating. These flares aren't just random outbursts, they're cosmic laboratories. The extreme conditions during a flare create matter and antimatter pairs, offering scientists a rare glimpse into quantum physics at energies impossible to replicate on Earth. Some researchers even speculate that these events could be the source of mysterious fast radio bursts, those fleeting intergalactic signals that have puzzled astronomers for years. What makes gamma-ray flares truly humbling is their unpredictability. Unlike pulsars, which tick like cosmic clocks, magnetars flare without warning, reminding us that the universe still holds plenty of surprises. And while we might never witness one up close, their distant brilliance serves as a stark reminder of the raw power lurking in the cosmos. So the next time you look up at the night sky, remember, somewhere out there, a magnetar could be gathering strength for its next spectacular light show. Shifting our gaze to another cosmic mystery, let's explore how these magnetic monsters might hold the key to unraveling one of astronomy's biggest puzzles: fast radio bursts. Now let's turn our attention to one of the most puzzling phenomena in the cosmos: fast radio bursts. These intense, millisecond-long blasts of radio waves have baffled scientists since their discovery, sparking wild theories ranging from alien transmissions to cosmic cataclysms. But in recent years, magnetars have emerged as prime suspects in solving this mystery. The connection between these ultramagnetic stars and fast radio bursts could rewrite our understanding of the universe's most enigmatic signals. The breakthrough came in April 2020 when astronomers witnessed something unprecedented. A magnetar within our own Milky Way, known as SGR 1935+2154, unleashed a fast radio burst. This was the first time an FRB had been traced back to a known object, and it was a game-changer. The burst itself was less energetic than those detected from distant galaxies, but its fingerprints matched perfectly, strong evidence that at least some fast radio bursts originate from magnetars. Imagine catching a cosmic criminal red-handed, finally linking a decades-old mystery to a tangible culprit. So how exactly could a magnetar produce these fleeting radio signals? One leading theory suggests that starquakes, those violent crust fractures we discussed earlier, might be the trigger. As the magnetar's surface shifts, its magnetic field lines snap and reconnect, launching a storm of particles and energy. This chaotic environment could generate the conditions needed for an FRB, like a lightning bolt of cosmic proportions. Another idea points to magnetars' magnetospheres, the intense magnetic bubbles surrounding them. Particles trapped in these fields could accelerate to near light speeds, emitting radio waves as they spiral wildly. It's like a natural particle collider, but one that operates with forces beyond anything we could recreate on Earth. Of course, not all fast radio bursts are created equal. Some repeat randomly, while others are one-off events. Some are incredibly powerful, suggesting different origins or mechanisms. This has led to competing theories, including the possibility that multiple cosmic phenomena, not just magnetars, could be responsible. For a while, the more exotic explanations like alien megastructures or collapsing black holes captured public imagination. But as evidence mounts, the magnetar hypothesis has gained serious traction, offering a more grounded solution to the puzzle. What makes this discovery so thrilling is its potential to unify two of astrophysics' biggest mysteries. If magnetars are indeed the source of at least some fast radio bursts, it could help us understand not just these fleeting signals, but also the extreme physics of magnetars themselves. Every new FRB detected could be another piece of the puzzle, revealing how these magnetic monsters behave under conditions we can barely fathom. As we continue to listen to the whispers of the cosmos, one thing is clear: magnetars are far more than just cosmic oddities. They're dynamic, violent, and endlessly fascinating laboratories that challenge our understanding of physics. And with each new burst, whether it's a gamma-ray flare or a fast radio signal, we're reminded that the universe still has plenty of secrets left to share. Up next, let's tackle the challenges astronomers face when trying to observe these elusive cosmic powerhouses. Now let's shift gears and talk about the real-world hurdles astronomers face when trying to study these cosmic powerhouses. Observing magnetars isn't like pointing a telescope at a nearby star and snapping a photo. It's more like trying to catch a lightning bolt in a bottle. These objects are incredibly rare, with only around 30 confirmed active magnetars in our entire galaxy. Even when we do find one, their bursts of activity can be frustratingly short-lived, sometimes lasting just milliseconds. Imagine trying to study a firework that explodes once every few years, and you only have a split second to capture it. That's the challenge scientists are up against. Adding to the complexity is the constant buzz of cosmic noise. The universe is filled with background radiation, interstellar dust, and signals from other celestial objects, all of which can drown out the faint or fleeting emissions from magnetars. It's like trying to hear a whisper in the middle of a roaring concert. To cut through the chaos, astronomers rely on specialized tools like the Chandra X-ray Observatory and the Neutron Star Interior Composition Explorer, or NICER. These instruments are fine-tuned to detect the high-energy X-rays and gamma rays that magnetars emit, acting like cosmic eavesdroppers tuned to the universe's most violent frequencies. One of the most fascinating techniques scientists use is listening to magnetars through their X-ray pulses. Just as a doctor uses a stethoscope to hear a heartbeat, astronomers analyze the rhythmic pulses of X-rays coming from these stars. Each pulse is a clue revealing details about the magnetar's rotation, magnetic field, and even the bizarre physics happening in its crust. For example, a sudden glitch in the pulse rate might signal a starquake, while changes in the pulse's intensity could hint at magnetic reconnection events. These tiny variations are like cosmic Morse code, helping us decode the inner workings of these extreme objects. But even with the best technology, magnetars keep throwing curveballs. Some go silent for years, only to flare up without warning. Others emit erratic bursts that defy existing models. This unpredictability means astronomers have to stay vigilant, constantly monitoring the skies for new activity. It's a bit like guarding a vault where the lock changes every few hours. You never know what you're going to find. What makes this detective work so rewarding, though, is the potential payoff. Every observation, every pulse brings us closer to understanding not just magnetars, but the fundamental laws of physics under conditions we can't replicate on Earth. These cosmic laboratories push the boundaries of what we know about matter, energy, and magnetism, and each challenge we overcome in observing them reveals a little more about the universe's most extreme environments. Next up, we'll take a closer look at the known magnetars within our own Milky Way and the unique behaviors that make each one a standout in the cosmic crowd. Now, let's turn our attention to the magnetars we've actually found right here in our cosmic backyard, the Milky Way. While these magnetic monsters are rare, astronomers have managed to identify a handful of them, each with its own quirks and mysteries. One of the most famous is SGR 1900+14, located roughly 20,000 light-years away in the constellation Aquila. This magnetar made headlines in 1998 when it unleashed a colossal flare so powerful it temporarily disabled several spacecraft. What makes SGR 1900+14 particularly fascinating is its periodic bursts of activity, almost like a cosmic alarm clock going off at unpredictable intervals. Then there's 1E 1048.1-5937, a magnetar nestled in the constellation Carina about 9,000 light-years from Earth. Unlike its more explosive siblings, this one is known for its eerie quietness, occasionally breaking its silence with faint X-ray whispers. But don't let its calm demeanor fool you. Back in 2007, it surprised scientists by producing a rare radio emission, a behavior typically seen in pulsars, not magnetars. This switching ability has made it a puzzle for researchers, blurring the line between these two types of neutron stars. Another standout is SGR 1806-20, arguably the most energetic magnetar ever observed. Situated about 50,000 light-years away in the constellation Sagittarius, this beast made history in 2004 with a flare so bright it briefly outshone the full moon. The burst was so intense it actually disturbed Earth's ionosphere, proving that even from halfway across the galaxy, magnetars can reach out and touch us. But magnetars aren't just scattered randomly across the Milky Way. Many of them are found near supernova remnants, the aftermath of the violent explosions that birthed them. Take 1E1 845.5-0245, located near the center of our galaxy. This magnetar is thought to be relatively young, just a few thousand years old, and its surroundings are still glowing from the heat of its formation. Studying it gives us a rare glimpse into the early life of these magnetic powerhouses. Now, here's a fun twist: some magnetars don't just stick to one type of emission. Take XTJ1 810-197, discovered in 2003. This one flips between emitting X-rays and radio waves, almost like a cosmic DJ switching between stations. This behavior challenges our understanding of how magnetars evolve and what triggers these shifts in their emissions. cataloging these objects isn't just about ticking boxes on a cosmic checklist. Each magnetar tells a unique story about the extremes of physics, from their violent births to their unpredictable tantrums. And as we uncover more about their locations, ages, and behaviors, we're not just mapping the Milky Way, we're piecing together the life cycle of some of the universe's most fascinating objects. Next, we'll venture beyond our galaxy to explore magnetars hiding in the cosmic depths, where the rules of physics might be even stranger. Stepping beyond the Milky Way, we find that magnetars don't just belong to our cosmic neighborhood, they're scattered throughout the universe, lurking in distant galaxies where their extreme behavior can teach us even more about these magnetic enigmas. Take the Large Magellanic Cloud, a satellite galaxy of our own Milky Way, roughly 160,000 light-years away. Here, astronomers have spotted magnetar candidates, their presence betrayed by sudden, brilliant flashes of X-rays and gamma rays. Because these bursts follow distinct patterns, sharp spikes followed by slower fading, scientists can pick them out from the cosmic noise, even across such vast distances. One standout example is the magnetar candidate in the remnants of supernova 1987A, the closest observed supernova explosion in modern history. While it hasn't been confirmed as a magnetar yet, the way its light curves behave, spiking unpredictably and then dimming, strongly suggests a hypermagnetic neutron star at work. These light curves act like cosmic fingerprints, helping astronomers distinguish magnetars from other celestial phenomena, like black holes or ordinary pulsars, even when they're millions of light-years away. But how do we know these distant bursts are coming from magnetars and not something else? The answer lies in their burst patterns. Magnetars don't just flare randomly, their outbursts often come in clusters, with multiple smaller bursts leading up to or following a major eruption. This signature behavior, combined with the unique way their X-ray emissions fade over time, makes them identifiable even in galaxies far beyond our own. For instance, in 2008, a magnetar-like burst was detected in the galaxy Messier 81, over 12 million light-years distant. The event's rapid rise and slow decay matched the profile of a magnetar flare, offering tantalizing evidence that these objects are universal, not just local phenomena. Supernova remnants play a crucial role in this cosmic detective work. Just like in the Milky Way, magnetars in other galaxies tend to form in the debris of exploded stars. The remnants act like glowing signposts, pointing astronomers toward potential magnetar nurseries. In the Small Magellanic Cloud, another nearby galaxy, researchers have found X-ray sources embedded in supernova remnants that flare up in ways reminiscent of magnetars. These environments, rich in swirling magnetic fields and dense matter, are perfect laboratories for studying how magnetars are born and evolve under different galactic conditions. What's truly mind-bending is that some of these extragalactic magnetars might be even more extreme than the ones we know. In 2019, a brief but incredibly bright X-ray burst was spotted in a galaxy over 400 million light-years away. The event, lasting less than a second, packed the energy of thousands of years' worth of solar output. While its origin is still debated, some scientists suspect it could be an ultra-rare, giant flare from a magnetar in a distant galaxy, proof that these objects can unleash staggering power across cosmic scales. Studying magnetars beyond the Milky Way isn't just about cataloging distant curiosities. It's a way to test whether the physics we've observed locally holds true in vastly different environments. Do magnetars in other galaxies behave the same way? Are their magnetic fields stronger or weaker? Answering these questions could reveal whether magnetars are universal oddities, or if the universe has even stranger magnetic monsters waiting to be discovered. Next, we'll push the boundaries further and ask, what if magnetars could get even more extreme? What theoretical extremes might lurk in the cosmos? Delving into the realm of the unimaginable, let's explore what might lie beyond the magnetars we know, hypothetical cosmic beasts with magnetic forces so intense they defy our current understanding of physics. Could there be ultra-magnetars lurking in the universe with fields even stronger than the quadrillions of Gauss we've measured so far? Theoretically, the answer might be yes. Some models suggest that under extreme conditions like the collision of two neutron stars' magnetic fields could briefly spike to incomprehensible levels, creating a transient ultra-magnetar. These fleeting monsters would dwarf even the most powerful magnetars we've observed, their fields so intense they could distort the very fabric of spacetime itself. But here's the catch: magnetic fields can't grow infinitely strong. At some point, the energy stored in the field would overwhelm the star's gravity, causing it to tear itself apart. This raises a tantalizing question: what happens when a magnetar's magnetic field crosses this critical threshold? One possibility is that the star collapses into an even stranger object, a quark star. Unlike neutron stars, where matter is crushed into neutrons, quark stars would be a soup of free-floating quarks, the fundamental building blocks of protons and neutrons. These exotic stars, if they exist, could represent the next stage in the life of an ultramagnetar, where magnetism and quantum forces reach a precarious balance. The extremes don't stop there. Some theories propose that ultramagnetars could warp spacetime so severely they create temporary magnetic wormholes, bridges between distant points in the universe. While this sounds like science fiction, the math suggests that under the right conditions, a magnetar's field could twist spacetime into a tunnel-like structure. These wormholes wouldn't be the cosmic shortcuts of movies. They'd be unstable, vanishing almost instantly. But for a brief moment, they'd offer a glimpse into how magnetism and gravity intertwine at the very edge of known physics. Science fiction has long played with these ideas, from magnetars powering apocalyptic weapons in The Core to their portrayal as cosmic time machines in Doctor Who. While these depictions take creative liberties, they're rooted in a kernel of scientific plausibility. Real-life ultramagnetars might not bend time or space on command, but they could push the boundaries of what we think is possible. Imagine a star so magnetic it could pull the iron from your blood thousands of light years away, or warp light into bizarre patterns visible across the universe. The search for these theoretical monsters isn't just about cataloging cosmic oddities. It's a test of whether our laws of physics hold up under the most extreme conditions. If we ever detect an ultramagnetar, it could force us to rewrite textbooks on quantum mechanics, relativity, and even the nature of matter itself. Until then, these hypothetical giants remain one of astrophysics' most thrilling mysteries, proof that the universe always has a way of surprising us. Next, we'll confront another mind-bending question: how do magnetars warp time itself? Now let's bend our minds around another astonishing effect of magnetars: their ability to warp time itself. According to Einstein's theory of general relativity, massive objects like magnetars don't just distort space, they also slow down time. The stronger the gravity, the more dramatic the effect. On a magnetar's surface, where gravity is billions of times stronger than Earth's, time doesn't just crawl, it practically grinds to a halt compared to our planet. Imagine placing two identical clocks side by side, one on Earth and the other on a magnetar. While the Earth-bound clock ticks away normally, the magnetar's clock would lag far behind. Calculations show that for every single second passing here, only a tiny fraction of that second would elapse near the magnetar's surface. To put numbers to it, if you could stand on a magnetar for what felt like just 5 minutes, decades would have flown by on Earth. This isn't science fiction, it's the universe enforcing its own rules, revealing how gravity and time are intimately linked. Fans of the movie Interstellar might recognize this concept. Near the film's fictional black hole, Gargantua, hours for the crew equaled years for those back home. Magnetars could produce a similar, albeit less extreme, version of this time dilation. While they're not as massive as black holes, their intense gravity still creates a noticeable time warp. For example, if astronauts somehow orbited a magnetar for a week, their return to Earth might find everyone decades older. It's a chilling reminder of how relativity isn't just abstract math, it's a force that shapes reality itself. But here's where things get even weirder. Magnetars don't just slow time, they twist it in ways that challenge our intuition. Their colossal magnetic fields interact with space-time so intensely that they could create localized pockets where time behaves unpredictably. Picture a whirlpool in a river where water flows differently at the edges versus the center. A magnetar's gravity might produce similar eddies in time, where clocks tick at different rates depending on their position relative to the star's poles or equator. This isn't just theoretical musing. In 2020, scientists studying a magnetar's X-ray pulses noticed tiny irregularities that could hint at these very distortions. While the evidence isn't definitive yet, it raises a thrilling possibility that magnetars aren't just cosmic magnets but natural time machines, offering us a laboratory to test Einstein's wildest predictions. So next time you glance at your watch, consider this. Time isn't the rigid, universal constant we often assume. Near a magnetar, it becomes fluid, stretching and compressing under the star's immense pull. It's a humbling thought, one that reminds us the universe still holds mysteries even our boldest theories can't fully explain. And speaking of mysteries, let's turn our attention to another gripping question. What would happen if Earth wandered too close to one of these magnetic monsters? Let's take a moment to step into a truly apocalyptic what-if scenario. Picture this: Earth, our pale blue dot, isn't nestled safely in the sun's gentle embrace, it's instead locked in orbit around a magnetar. At first glance, the night sky would be breathtaking. Auroras, normally confined to polar regions, would dance across the entire planet, even in broad daylight, painting the heavens in otherworldly hues. But this spectacle would come at a horrifying cost. The magnetar's magnetic field, quadrillions of times stronger than Earth's, would warp the very fabric of matter around us. Credit cards would demagnetize instantly. Metal objects, cars, bridges, even the steel frames of buildings would twist and shatter as atomic bonds are violently rearranged. The planet's magnetic field, our shield against solar radiation, would be utterly overwhelmed, leaving us exposed to deadly cosmic rays. Within days, radiation sickness would sweep across the globe, and electronic infrastructure would fail catastrophically as surges fry circuits worldwide. Then there's the Starquakes. When a magnetar's crust fractures, it releases pent-up energy in bursts of X-rays and gamma rays. A single such flare from 50,000 light-years away once ionized Earth's upper atmosphere in 2004. Now imagine that happening right next door. These eruptions would bathe our planet in lethal radiation, sterilizing the surface and vaporizing the ozone layer. Any life clinging on would face a cascade of extinctions, with DNA shredded by the relentless bombardment. And let's not forget, time itself would betray us. As we saw earlier, a magnetar's gravity bends time so severely that a single Earth year might feel like mere hours on its surface. But for a planet orbiting one, the effects would be chaotic. Tidal forces would stretch and compress the globe, triggering perpetual earthquakes and volcanic eruptions. The very rotation of Earth could slow or accelerate unpredictably, making day and night meaningless as the planet groans under the strain. This nightmare scenario throws into sharp relief just how delicate the conditions for life truly are. Astronomers hunting exoplanets often focus on the habitable zone, the orbital distance where liquid water can exist. But a magnetar's habitable zone, it's a contradiction in terms. No atmosphere could endure, no biology could adapt. Even extremophiles, Earth's hardiest organisms, would stand no chance against such relentless physics. Yet there's a twisted silver lining here. By studying these impossible environments, we gain a deeper appreciation for our own fragile oasis. The same forces that would obliterate us also forged the heavy elements in our bones and the iron in our blood. Magnetars, in their terrifying grandeur, remind us that the universe isn't just indifferent, it's capable of extremes we can scarcely fathom. And that realization makes the quiet stability of our solar system feel like the rarest of cosmic gifts. Now, having glimpsed the destructive power of these magnetic monsters, you might wonder, how do they stack up against their even more infamous cousins, black holes? That's a showdown we'll dive into next, shifting our gaze from the real-world horrors of magnetars to their fictional counterparts. It's fascinating to see how these cosmic monsters have sparked the imaginations of storytellers. Science fiction often takes the terrifying power of magnetars and amplifies it, bending reality for dramatic effect, but sometimes the truth is stranger than fiction. Take the 2003 disaster film The Core, where a team of scientists must restart Earth's stalled magnetic field by detonating nuclear bombs in the planet's core. While the movie takes wild liberties, Earth's core doesn't just stop, and the solution is pure fantasy. It taps into real fears about magnetic catastrophes. A magnetar's influence isn't far off from the film's premise, just scaled to an even more extreme level. Then there's Doctor Who, where the Time Lords once weaponized magnetars to rewrite the laws of physics in their time war. The show cleverly plays with the idea of magnetic fields distorting reality, something that aligns, at least loosely, with how magnetars actually warp spacetime. The science is stretched, of course, but the core concept isn't entirely pulled from thin air. Video games, on the other hand, often strive for a mix of spectacle and authenticity. In Elite Dangerous, players can navigate to simulated magnetars, their ships buffeted by intense radiation as they approach. The game mimics real physics. Getting too close risks catastrophic system failure, forcing pilots to carefully manage their approach. It's a rare case where entertainment doesn't shy away from the genuine dangers these objects pose. But pop culture doesn't always get it right. Many depictions treat magnetars like all-purpose doomsday devices, ignoring the nuances of their behavior. Starquakes and gamma-ray bursts, for instance, are often shown as instantaneous extinction-level events, when in reality, their impact depends heavily on distance and angle. The 2004 Magnetar flare that affected Earth, for example, was disruptive but not apocalyptic because it originated halfway across the galaxy. Still, these creative liberties serve a purpose. By exaggerating magnetar's power, sci-fi makes their real-world counterparts even more awe-inspiring. When you learn that a fictional spaceship was torn apart by magnetic forces, then discover that real magnetars could indeed do that, just from much farther away, the facts hit harder. So, the next time you encounter a magnetar in a movie or game, enjoy the spectacle, but remember, the truth is out there and it's every bit as thrilling. Now, with our imaginations thoroughly stretched, let's turn to an even wilder question. Could humanity ever harness the raw power of a magnetar? That's a frontier we'll explore next. Now, let's venture into a thought experiment that stretches the limits of human ingenuity. Could magnetars, these cosmic powerhouses, ever become the ultimate energy source for advanced civilizations? The idea might sound like science fiction, but when we push the boundaries of physics, it's worth exploring just how plausible or perilous this could be. Imagine constructing a Dyson sphere, a megastructure designed to harness a star's energy, but around a magnetar instead of a sun. Theoretically, capturing even a fraction of a magnetar's magnetic or rotational energy could provide near limitless power. A single magnetar emits enough energy in 1 second to meet Earth's needs for billions of years. The potential is staggering, but so are the obstacles. First, there's the issue of distance. The nearest known magnetar sits thousands of light years away, making transportation and construction a logistical nightmare. Even if we could travel such distances, the extreme environment near a magnetar would pose existential risks. Its magnetic field could shred any machinery or living tissue long before a Dyson sphere could be assembled. Then there's the radiation gamma-ray flares and X-ray bursts would fry any energy-collecting infrastructure unless shielded by hypothetical materials far beyond our current technology. Energy containment is another hurdle. Magnetars don't emit steady, predictable power like stars. Their output comes in violent, erratic bursts. Storing and regulating that energy would require systems capable of handling sudden, colossal surges without catastrophic failure. Compare this to more tame, futuristic energy proposals like fusion reactors or black hole energy harvesting. Fusion, while challenging, offers controllable reactions, and black holes, though equally distant, emit more consistent Hawking radiation over time. Magnetars, by contrast, are the universe's unpredictable power plants, yet the allure persists. If a civilization could master magnetar energy, the rewards would dwarf anything achievable with conventional sources. Picture a society capable of powering interstellar travel, megascale computing, or even manipulating spacetime itself. Some theories suggest advanced beings might use magnetars as natural particle accelerators, unlocking physics we can't yet fathom. Of course, this remains speculative. For now, magnetars serve better as natural laboratories for testing extreme physics than as power grids. But the exercise forces us to think bigger, beyond the confines of our planetary thinking. Whether humanity ever taps into such power is uncertain, but the mere possibility reminds us how much universe is left to explore and exploit. With that cosmic challenge laid bare, let's turn to an even more explosive scenario: what happens when magnetars collide? The resulting fireworks could rewrite our understanding of the cosmos. Now, let's shift our gaze to one of the universe's most spectacular events, a collision between a magnetar and another neutron star. Picture this cosmic dance of destruction, where two incredibly dense objects spiral toward each other, warping spacetime itself before unleashing an explosion that outshines entire galaxies. The aftermath isn't just a visual spectacle, it's a forge for the very elements that make up our world. When a magnetar crashes into another neutron star, the impact generates a kilonova, an explosion so powerful it briefly rivals the brightness of a supernova. Unlike a typical supernova, though, a kilonova spews out vast amounts of heavy elements like gold, platinum, and uranium. These aren't just random byproducts, they're the building blocks of planets, jewelry, and even life itself. Scientists estimate that a single kilonova can produce hundreds of Earth masses worth of gold alone. That's right, the ring on your finger likely owes its existence to a cataclysmic collision that happened billions of years ago. But the drama doesn't stop there. The collision sends ripples through the fabric of spacetime, known as gravitational waves. Facilities like LIGO, the Laser Interferometer Gravitational Wave Observatory, have already detected waves from neutron star mergers. Adding a magnetar to the mix would amplify these signals, creating distortions so intense they'd push our detection capabilities to the limit. The magnetic fields involved could also twist the gravitational waves in unique ways, offering clues about the magnetar's structure and the extreme physics at play. These collisions don't just create elements, they scatter them across the cosmos. Magnetars, with their ultra-strong magnetic fields, might act like cosmic catapults, hurling heavy metals far and wide. This could explain why certain regions of space are richer in gold and platinum than others. It's a messy, violent process, but one that seeds galaxies with the ingredients for future solar systems, and perhaps even life. What's truly fascinating is how magnetar collisions could reshape our understanding of galactic chemistry. Most heavy elements were thought to come from supernova, but kilonovas are now recognized as major players. If magnetars are involved, their magnetic fields might accelerate particles to unimaginable speeds, creating even rarer elements or exotic states of matter we've yet to discover. As we piece together these cosmic puzzles, each collision reminds us of the universe's unrelenting creativity. From the gold in our electronics to the platinum in our lab equipment, we're literally holding pieces of these ancient explosions in our hands. And with every new kilonova detected, we get closer to unraveling how magnetars shape the cosmos one cataclysmic crash at a time. With that in mind, let's turn to another chapter in the life of these magnetic giants, how they age, decay, and eventually fade into the darkness of space. Turning our attention from cosmic collisions to the quieter, yet equally fascinating, journey of these magnetic giants, let's explore the life cycle of a magnetar. Born in the fiery chaos of a supernova, their story doesn't end with that explosive beginning. Instead, it unfolds over millennia, shaped by forces so extreme they defy imagination. A magnetar's youth is marked by incredible violence. In the first few thousand years after its birth, it's a restless powerhouse crackling with energy. Its magnetic field, trillions of times stronger than Earth's, drives frequent starquakes and gamma-ray flares, lighting up the cosmos like a cosmic lighthouse on overdrive. But even the strongest magnets don't last forever. Over tens of thousands of years, that unbelievable magnetic field begins to weaken. The starquakes become less frequent, the flares less intense, and the magnetar starts to quiet down. As the eons pass, a magnetar enters middle age. Its once unruly magnetic field decays, though it's still far stronger than any ordinary neutron stars. The star's rotation, which might have started at a dizzying hundreds of times per second, gradually slows. Unlike pulsars, which can spin steadily for millions of years, magnetars lose their energy much faster. Their magnetic fields act like cosmic brakes, sapping their rotational energy and converting it into radiation. This is why we detect far fewer old magnetars than pulsars. Many have already faded into obscurity by the time we'd notice them. Eventually, a magnetar reaches its twilight years. After hundreds of thousands or even millions of years, its magnetic field weakens to the point where it no longer powers dramatic flares or starquakes. It becomes what astronomers call a dead magnetar, a dormant neutron star, still incredibly dense, but now quiet and dark. Without its signature bursts of energy, it blends into the backdrop of the universe, indistinguishable from other aged neutron stars unless we happen to catch its faint X-ray glow. But here's where magnetars and pulsars diverge. Pulsars, born with weaker magnetic fields, spin down much more slowly. Some pulsars remain active for tens of millions of years, their steady pulses acting like cosmic metronomes. Magnetars, by contrast, burn bright and fast, like celestial fireworks that blaze brilliantly but briefly. This difference helps explain why pulsars are far more common in our galaxy. They simply have longer lifespans. Yet even in death, magnetars leave a legacy. Their intense magnetic fields may have scattered heavy elements across space, and their bursts of radiation could have influenced the chemistry of nearby planets. Some theories even suggest that dormant magnetars might occasionally reawaken, their magnetic fields somehow re-energized by unknown processes. The life cycle of a magnetar is a reminder that even the most extreme objects in the universe are subject to time. From their explosive births to their quiet ends, they shape the cosmos in ways we're only beginning to understand. And as we continue to study these magnetic marvels, each discovery peels back another layer of their mystery. Now, let's venture into the realm of speculation where science meets the unknown, and ask whether magnetars could hold clues to one of the universe's greatest enigmas, dark matter. Exploring the edges of cosmic understanding, we now turn to one of the most puzzling questions in modern astrophysics. Could magnetars hold the key to unraveling the mystery of dark matter? While this connection remains speculative, the extreme nature of these magnetic monsters makes them fascinating candidates for testing some of the universe's deepest secrets. Dark matter, that invisible substance making up roughly 85% of the universe's mass, has eluded direct detection for decades. Its presence is inferred only through its gravitational tug on galaxies and galaxy clusters. But what if magnetars, with their unimaginably strong magnetic fields, could act as cosmic traps or detectors for dark matter particles? Some theorists propose that certain hypothetical dark matter particles, like actions or weakly interacting massive particles, might interact with these intense magnetic environments in detectable ways. Here's where it gets intriguing. A study published in the journal Physical Review Letters suggested that Magnetar bursts could indirectly reveal dark matter. The idea hinges on a process called the Primakov effect, where actions a leading dark matter candidate might convert into photons under extreme magnetic conditions. If this happens near a magnetar, the resulting energy release could leave a faint but distinctive fingerprint in its X-ray or gamma-ray emissions. In other words, magnetars might inadvertently be broadcasting signals of dark matter interactions if we know how to look for them. But it's important to distinguish between peer-reviewed science and bold speculation. While some research teams have modeled these interactions with rigorous mathematics, no concrete evidence has yet linked magnetar activity to dark matter. Other theories suggest that dark matter particles could accumulate in a magnetar's core over time, eventually triggering starquakes or flares when their density reaches a critical point. These ideas remain on the fringe, but they're not dismissed outright, because in astrophysics, sometimes the wildest hypotheses lead to the biggest breakthroughs. Skeptics argue that dark matter's ghostly nature makes direct interaction with magnetars unlikely. After all, if dark matter truly doesn't interact with ordinary matter except through gravity, then even a magnetar's monstrous magnetic field might not be enough to influence it. Yet proponents counter that extreme environments could reveal exceptions to the rules, much like how black holes unveiled new physics at the edge of Einstein's theories. What makes this discussion so compelling is the sheer scale of possibility. Magnetars are natural laboratories for conditions we can't replicate on Earth. Whether or not they unlock the dark matter puzzle, studying how their magnetic fields interact with hypothetical particles pushes the boundaries of our knowledge. Future telescopes, like the European Space Agency's Athena X-ray Observatory, could provide data to test these theories, either confirming a radical connection or steering scientists toward new avenues. As we venture deeper into the quantum mysteries of the cosmos, magnetars remind us that the universe's greatest secrets often hide in plain sight, just waiting for the right tools, the right minds, and the right magnetic monsters to reveal them. Now, let's zoom in even closer to these stellar powerhouses and examine the bizarre quantum effects unfolding within their crusts, where physics as we know it gets twisted into entirely new shapes. Now, let's peel back the layers of a magnetar's crust, where the laws of physics take a surreal turn. Imagine squeezing matter so tightly that atomic nuclei lose their familiar shapes, morphing into bizarre, noodle-like structures. This isn't science fiction, it's the reality inside a magnetar's crust, where pressures are so extreme that protons and neutrons arrange themselves into what physicists whimsically call cosmic pasta. Picture spaghetti strands, lasagna sheets, or even gnocchi-like clumps, all forged in a cauldron of unimaginable density. This cosmic pasta isn't just a quirky detail, it's a game-changer for how magnetars behave. In ordinary matter, atomic nuclei are neatly spaced spheres, but under the crushing weight of a magnetar's gravity, those spheres get flattened and stretched into elongated shapes. These deformed nuclei create a chaotic, slippery environment where the crust stability hangs by a thread. Think of it like trying to build a house on a foundation of wet noodles. Any shift or stress could trigger a catastrophic collapse. And in a magnetar's case, that collapse isn't just a local event. It sends shockwaves through the star's magnetic field, potentially unleashing the violent starquakes we've observed from light years away. Here's where quantum mechanics enters the spotlight. The bizarre arrangement of nuclei in the crust affects how electrons move, or more accurately, how they don't move. In normal materials, electrons flow freely, creating currents that generate magnetic fields. But in a magnetar's crust, electrons are forced into a quantum state called Landau quantization, where they can only orbit in specific, restricted paths dictated by the star's monstrous magnetic field. This constrained movement makes the crust both a conductor and an insulator at the same time, a paradox that amplifies magnetic energy to staggering levels. The consequences are dramatic. When the crust's poster-like layers fracture under stress, they release pent-up magnetic energy in bursts so powerful they can ripple space-time itself. These starquakes aren't just seismic events, they're cosmic power surges that can briefly outshine entire galaxies. For instance, the 2004 flare from Magnetar SGR 1008-10620, likely triggered by a crustal rupture, released more energy in a tenth of a second than our Sun emits in 150,000 years. That's the sheer scale of chaos brewing beneath a Magnetar's surface. What's even more mind-bending is how these quantum effects might solve a long-standing puzzle: why some Magnetars flare more frequently than others. Researchers suspect that the thickness and chewiness of their cosmic poster layers play a key role. A crust with softer, more fluid-like noodles might absorb stress without breaking, while a brittle, overcooked lasagna crust could shatter easily, leading to frequent outbursts. It's a delicate balance between rigidity and plasticity, governed by quantum rules we're still deciphering. As we probe deeper, Magnetars challenge our understanding of matter itself. Laboratories on Earth can't replicate the conditions inside these stars, making them irreplaceable natural experiments. Future missions like NASA Imaging X-ray Polarimetry Explorer aim to study the polarization of X-rays from Magnetar flares, offering clues about their crustal structure. Each burst we detect is like a cosmic telegram, encoded with secrets about how matter behaves when pushed to its absolute limits. So the next time you twirl spaghetti on your fork, remember, there's a version of that noodle, infinitely denser and stranger, shaping the most violent and magnetic objects in the universe. And with every starquake, these cosmic kitchens are cooking up new mysteries for us to unravel. Now, let's shift our gaze to the tools astronomers use to measure these invisible giants, where ingenuity meets the impossible. But how do we even begin to measure something as unfathomably powerful as a Magnetar's magnetic field? After all, we can't exactly stick a compass next to these cosmic monsters. So astronomers have gotten creative, developing ingenious ways to study these invisible forces from across the galaxy. One key technique involves listening to the rhythmic pulses of X-rays that Magnetars emit like cosmic heartbeats. As the star spins, its magnetic field channels radiation into beams that sweep past Earth like a lighthouse. By tracking tiny changes in the timing of these pulses, scientists can detect how the star's rotation slows down over time, a direct result of its magnetic field sapping energy from the star's spin. It's like watching a top gradually wobble to a stop, except this top weighs more than our Sun and is wrapped in a magnetic vise. For example, Magnetar 1E 2002, 159 plus 586 slows by about 1 millisecond every 7 years, revealing a magnetic field strength of roughly 2 trillion times Earth. But the real magic happens when we examine the X-rays themselves. Deep within a Magnetar's atmosphere, protons spiral around magnetic field lines, emitting radiation at specific frequencies called proton cyclotron lines. These lines act like cosmic barcodes. Their spacing and intensity betray the strength of the magnetic field crushing them. Imagine strumming a guitar string and adjusting the tension. The pitch changes just like these X-ray frequencies shift under a Magnetar's extreme magnetism. When researchers analyzed emissions from SGR 1806-20, they found proton cyclotron lines pointing to a field strength that could strip atoms apart at 1,000 kilometers away. Now here's where things get even more cutting edge. Light from Magnetars doesn't just carry information about its brightness or frequency. It's also polarized, meaning its electric waves vibrate in preferred directions. This polarization is like a secret handwriting left by magnetic fields, twisted and warped as light fights its way through the star's violent surroundings. That's why missions like NASA Imaging X-ray Polarimetry Explorer, or IXP, are game changers. By measuring X-ray polarization with unprecedented precision, IXP can map the chaotic magnetic geometry around magnetars in ways never before possible. Think of it as putting on polarized sunglasses that don't just reduce glare, but reveal the hidden structure of magnetic storms light years away. What makes these measurements so revolutionary is that they peer beyond simple numbers. Traditional methods give us field strengths, but polarization shows us how those fields twist, tangle, and reconnect, a crucial clue for understanding why magnetars erupt in flares and starquakes. For instance, if IXP detects highly twisted polarization patterns from a magnetar, it could mean the star's crust is seconds away from another catastrophic rupture. It's like reading the tremors before an earthquake, but on a cosmic scale. Yet even our best tools have limits. Magnetar emissions are often drowned out by cosmic noise or obscured by interstellar dust. Sometimes their bursts are so sudden and unpredictable that telescopes miss the critical first moments. That's why astronomers are designing next-generation detectors with faster reaction times and wider energy ranges, hoping to catch these magnetic giants in the act. So while we may never plant a flag on a magnetar's surface, the light we capture from these distant beasts carries fingerprints of their impossible magnetism. Every X-ray pulse, every polarized photon is a piece of the puzzle, helping us decode the universe's most extreme magnetic environments. And as our tools grow sharper, who knows what other magnetic marvels we'll uncover. Next, let's see how these terrifying objects stack up against their cosmic cousins in the neutron star family. Now, stepping back to see the bigger picture, let's explore where magnetars fit in the grand cosmic family of neutron stars. Imagine neutron stars as siblings, each with their own wild personalities and extreme behaviors. Magnetars are the rebellious ones, unpredictable, bursting with energy and wielding magnetic fields that dwarf everyone else's. But they're not alone in this cosmic household. First, meet the pulsars, the orderly siblings of the neutron star family. These stars are like cosmic metronomes, spinning at incredibly steady rates and beaming radiation in precise pulses. Some rotate hundreds of times per second, earning the nickname millisecond pulsars. Their magnetic fields, while still intense, around 1 trillion times stronger than Earth's, are tame compared to a magnetar's. Pulsars are the reliable lighthouses of the universe, their rhythmic flashes helping astronomers map the galaxy and even test Einstein's theory of relativity. Then there are the central compact objects, or CCO, the quiet, mysterious cousins. These neutron stars live in the remnants of supernova, but emit mostly in X-rays without the dramatic bursts or pulses of their siblings. Their magnetic fields are surprisingly weak for neutron stars, barely 1 billion times Earth's. Scientists think they might be magnetars in hiding, their fields buried under their surfaces or slowly decaying over time. But magnetars, they're the storm chasers of the family. While pulsars tick away with clockwork precision, magnetars crack under pressure, literally. Their crusts snap in starquakes, unleashing flares that can outshine entire galaxies for a split second. Their magnetic fields aren't just stronger, they're twisted, chaotic, and capable of reshaping the very atoms around them. While a typical pulsar's field might last for millions of years, a magnetar's fury often burns out in just a few millennia, leaving behind a quieter neutron star or even a CCO. Here's the fascinating part: some neutron stars switch identities. Take PSRJ 1119-6127, a star that started as a magnetar, flaring violently, only to calm down and behave like a regular pulsar. Others, like XTJ 1810-197, went quiet for years before suddenly reawakening with magnetar-like outbursts. It's as if these stars have multiple personalities, shifting between phases depending on how their interiors churn and their magnetic fields evolve. What ties this family together is their origin. All neutron stars are born from the collapsed cores of massive stars, but like siblings raised in the same house, their lives take wildly different paths. Pulsars are the disciplined athletes, CCOs the enigmatic introverts, and Magnetars the tempestuous artists. Yet each one offers a unique window into the extremes of physics, from gravity to magnetism to quantum mechanics. So next time you hear about a neutron star, ask yourself, which member of the family is it? The steady pulsar, the quiet observer, or the magnetic rebel? Each has a role to play in unraveling the universe's secrets, and as we'll see next, even among these extremes, magnetars stand out as the rarest and most dangerous of them all. Now, let's tackle a question that might be lingering in your mind. Just how rare are magnetars in the vastness of our galaxy? The answer is a cosmic twist of irony. They are both everywhere and nowhere at once. Statistically speaking, astronomers estimate there could be as many as 30 million dormant magnetars lurking in the Milky Way. That's one for every 10 ordinary stars in our galactic neighborhood. But here's the catch. Only about 30 of these magnetic monsters have been confirmed as active magnetars. That's like having a stadium packed with thousands of people, but only a handful are shouting loud enough to be heard. So why the dramatic gap between potential and detection? For starters, magnetars are cosmic introverts. Their most extreme outbursts, those jaw-dropping flares and starquakes, are fleeting, lasting mere seconds or minutes. Imagine trying to spot a firefly in a thunderstorm. Unless it flashes at just the right moment, you'll miss it entirely. Most magnetars spend centuries or even millennia in quiet slumber, their magnetic fields slowly decaying until they fade into obscurity. Then there's the challenge of their emissions. Active magnetars primarily announce themselves through X-rays and gamma rays, which are atmosphere blocks. That means we need space-based telescopes like Chandra or Fermi to catch their signals. Even then, these instruments have to be pointed in the right direction at the exact moment a magnetar decides to throw a tantrum. It's no wonder so many slip through our cosmic net, but the scarcity of observed magnetars isn't just a detection issue, it's a clue about their lifespan. Unlike pulsars, which can keep ticking for millions of years, magnetars burn bright and fast. Their magnetic fields are so intense that they bleed energy at a staggering rate, often quieting down within 10,000 years. That's a blink in cosmic time, making active magnetars the mayflies of the neutron star world. What does this mean for our galaxy? Magnetars might be rare in visibility, but their impact is outsized. Every flare injects energy into interstellar space, influencing the birth of new stars and the chemistry of nebulae. Their fleeting existence also suggests that the Milky Way's youth was far more violent than today, with magnetar eruptions lighting up the galactic night like fireworks. And here's a tantalizing thought. Many of those 30 million dormant magnetars could be hiding in plain sight. Some might masquerade as ordinary pulsars or CCOs, their magnetic skeletons buried beneath calm exteriors. Others could be the unseen engines behind mysterious cosmic phenomena, like fast radio bursts or gamma-ray glows. So while magnetars might seem like cosmic unicorns, they're more like icebergs. What we've spotted is just the tip of a hidden magnetic universe. And as our telescopes grow sharper, we're poised to uncover more of these elusive giants, rewriting the story of our galaxy one flare at a time. Now, let's peer into the cosmic crystal ball and explore what the future holds for magnetar research. The next generation of telescopes is set to revolutionize our understanding of these magnetic monsters, unveiling secrets that have eluded us for decades. Leading the charge is the Athena spacecraft, slated to launch in the 2030s. This cutting-edge X-ray observatory will be a game-changer, armed with instruments sensitive enough to detect the faint whispers of dormant magnetars. Imagine tuning into a radio station that's been static for centuries. Athena could pick up the weak X-ray pulses of aging magnetars, revealing how their magnetic fields evolve over time. It's like having a time machine to study their life cycle in unprecedented detail. Then there's the Lynx X-ray Observatory, another powerhouse in development. Lynx will boast resolution so sharp it could spot a Magnetar's surface features, something no telescope has achieved before. Picture mapping the cracks in a Magnetar's crust during a starquake or watching magnetic field lines twist and snap in real time. These observations could finally answer lingering questions about how Magnetars unleash their colossal flares, knowledge that might even help us predict solar storms here on Earth. But the real excitement lies in the mysteries these tools could crack. Take fast radio bursts, those enigmatic cosmic signals that have puzzled astronomers for years. Thanks to a Magnetar in our own galaxy caught emitting an FRB in 2020, we now have a smoking gun linking the two phenomena. Future telescopes could catch Magnetars in the act more often, unraveling whether all FRBs stem from these magnetic beasts or if other cosmic players are involved. Quantum gravity, one of physics' biggest unsolved puzzles, might also find answers in Magnetar research. Their crushing gravity and intense magnetic fields create conditions so extreme they warp spacetime itself. By studying how light behaves near magnetars, scientists could test theories that unite quantum mechanics and general relativity, experiments impossible to replicate in any lab on Earth. And let's not forget the wild cards. What if we discover magnetars with magnetic fields beyond what we thought possible, or stumble upon a magnetar orbiting a black hole, creating a cosmic dance of unimaginable energy? Every new observation could rewrite the textbooks. The bottom line, we're on the brink of a golden age in magnetar science. With these next-gen telescopes as our guides, we're not just observing the universe, we're decoding its most magnetic mysteries, one brilliant flare at a time. So, let's take a step back and marvel at what we've uncovered about these cosmic powerhouses. Magnetars are truly the universe's ultimate magnetic monsters, with fields so strong they could strip the data from every credit card on Earth in an instant. They're not just destructive, they're cosmic lighthouses, sending out beams of X-rays and gamma rays that pierce the darkness of space, guiding astronomers to some of the universe's most extreme physics. And let's not forget their role as galactic alchemists. Through starquakes and flares, they might even be forging heavy elements like gold and platinum, sprinkling them across the cosmos like celestial treasure. But here's the thing, every discovery about magnetars only deepens the mystery. What else lurks in the magnetic dark? Are there even more extreme versions of these objects waiting to be found with fields beyond our current understanding? Could they hold clues to the nature of dark matter or the fabric of spacetime itself? The more we learn, the more questions arise, and that's the beauty of science. Now we want to hear from you. What's your favorite mind-blowing fact about magnetars? Maybe it's how a single flare can outshine the moon, or how their crusts resemble cosmic lasagna under unimaginable pressure. Drop your thoughts in the comments below. We're all part of this cosmic conversation. And if you've enjoyed this journey through the magnetic extremes of the universe, don't forget to hit that like button and subscribe. Stay curious, because the universe always has another secret to reveal. Until next time, keep looking up.